Hello, welcome back. I'm John, an old YouTuber. We have a new day today. It's Thursday, day before Friday. I record a lot of Danish video the whole day. I'm not finished reading the central processing units. I got to page 13. But soon it's 4 p.m. So let's try to finish. So actually I just like to go to bed and relax and read. Then watch Star Trek on Netflix. But this camcorder has charging the whole night and half the day, so we have a lot of power on the camcorder. Like 2.5 hours. So let's read something long, maybe something longer. But let's finish the CPU. I'm very thirsty. But this water is very cold because it's inside here. I cannot drink it so fast because it's very cold. So I cannot just swallow the water because it's hurting inside my mouth a little bit. So let's go to bed and read, try to finish central processing units. And I have all my read list there. Just find, maybe continue to do the 65 nanometers and 90. Continue this. I'll just find something else. Could read, look at that later, but first let's finish this. And I need a minute. I need a minute to do myself ready in my bed, and sound is 50. I need my fleece jackets on. So I have to stand up to get my fleece jacket on. Of course I'm freezing a little bit. I have recorded a lot of video today, but that's in my language Danish. Nobody is watching. Yes, I have to turn my small bed table. Go to my bed. So now I will just relax and read this. So let's start from the top, page 13. Let's continue. I not understand much of this, but I like to read it anyway, even I not understand it. I like to read about it, because next time I maybe understand a little bit more.
Interface, or Instruction Set Architecture, ISA. The strategy of the very long instruction word, VLI, causes some ILP to become implied directly by the software, reducing the CPU's work in boosting ILP and thereby reducing design complexity. Task level parallelism. Another strategy of achieving performance is to execute multiple threads or processes in parallel. This area of research is known as parallel computing. 71. In Flynn's taxonomy, This strategy is known as multiply instruction stream, multiple data stream, MIMD. 72. One technology used for this purpose was multiprocessing, MP. 73. The initial flavor of this technology is known as symmetric multiprocessing, SMP, where a small number of CPUs share a coherent view of their memory system. In this scheme, each CPU has additional hardware to maintain a constantly up-to-date view of memory. By avoiding stale views of memory, the CPUs can cooperate on the same program and programs can migrate from one CPU to another. To increase the number of cooperating CPUs beyond a handful, schemes such as non-uniform memory access, NUMA, and directory-based coherence protocols were introduced in the 1990s. SMP systems are limited to a small number of CPUs while NUMA systems have been built with thousands of processors. Initially, multiprocessing was built using multiple discrete ECPAS and boards to implement the interconnect between the processors. When the processors and their interconnect are all implemented on a single chip, the technology is known as chip-level multiprocessing, CMP, and the single chip as a multi-core processor. It was later recognized that finer-grain parallelism existed with a single program. A single program might have several threads, or functions, that could be executed separately or in parallel. Some of the earliest examples of this technology implemented input/output processing such as direct memory access as a separate thread from the computation thread. A more general approach to this technology was introduced in the 1970s when systems were designed to run multiple computation threads in parallel. This technology is known as multithreading, MOUNT. This approach is considered more cost-effective than multiprocessing, as only a small number of components within a CPU is replicated to support MOUNT as opposed to the entire CPU in the case of MP. In MOUNT, the execution units and the memory system including the caches are shared among multiple threads. The downside of MOUNT is that the hardware support for multithreading is more visible to software than that of MP, and thus supervisor software like operating systems have to undergo larger changes to support MOUNT. One type of MOUNT that was implemented is known as temporal multithreading, where one thread is executed until it is stored waiting for data to return from external memory. In THISM, the CPU would then quickly context switch to another thread which is ready to run. The switch often done in one CPU clock cycle, such as the Ultra SPARCT1. Another type of MOUNT is simultaneous multithreading, where instructions from multiple threads are executed in parallel within one CPU clock cycle. For several decades from the 1970s to early 2000s, the focus in designing high-performance general-purpose CPUs was largely on achieving high ILP through technologies such as pipelining, caches, superscalar execution, out-of-order execution, etc. This trend culminated in large, power-hungry CPUs such as the Intel Pentium 4. By the early 2000s, CPU designers were thwarted from achieving higher performance from ILP techniques due to the growing disparity between CPU operating frequencies and main memory operating frequencies, as well as escalating CPU power dissipation owing to more esoteric ILP techniques. CPU designers then borrowed ideas from commercial computing markets such as transaction processing, where the aggregate performance of multiple programs, also known as throughput computing, was more important than the performance of a single thread or process. This reversal of emphasis is evidenced by the proliferation of dual and more core processor designs, and notably, Intel's newer designs resembling its less superscalar 6P architecture. Late designs in several processor families exhibit CMP, including the x86-64 Optron and Athlon 64X2, the SPARC Ultra SPARCT1, IBM Power 4 and Power 5. as well as several video game console CPUs like the Xbox 360's triple-core PowerPC design, and the PlayStation 3's 7-core cell microprocessor. Data parallelism. A less common but increasingly important paradigm of processors, and indeed, computing in general, deals with data parallelism. The processors discussed earlier are all referred to as some type of scalar device. J, as name implies, vector processors deal with multiple pieces of data in the context of one instruction. This contrasts with scalar processors, which deal with one piece of data for every instruction. Using Flynn's taxonomy, these two schemes of dealing with data are generally referred to as single instruction stream, multiple data stream, SIMD, and single instruction stream, single data stream, SISD, respectively. The great utility in creating processors that deal with vectors of data lies in optimizing tasks that tend to require the same operation, for example, a sum or a dot product, to be performed on a large set of data. Some classic examples of these types of tasks include multimedia applications, images, video and sound, as well as many types of scientific and engineering tasks. Whereas a scalar processor must complete the entire process of fetching, decoding and executing each instruction and value in a set of data, a vector processor can perform a single operation on a comparatively large set of data with one instruction. This is only possible when the application tends to require many steps which apply one operation to a large set of data. Most early vector processors, such as the Cray-1, were associated almost exclusively with scientific research and cryptography applications. However, as multimedia has largely shifted to digital media, the need for some form of SIMD in general-purpose processors has become significant. Shortly after inclusion of floating-point units started to become commonplace in general-purpose processors, specifications for and implementations of SIMD execution units also began to appear for general-purpose processors. Some of these early SIMD specifications, like HP's Multimedia Acceleration Extensions, MAX, and Intel's MMX, were integer only. This proved to be a significant impediment for some software developers, since many of the applications that benefit from SIMD primarily deal with floating-point numbers. Progressively, developers refined and remade these early designs into some of the common modern SIMD specifications, which are usually associated with one instruction set architecture, ISA. Some notable modern examples include Intel's Streaming SIMD Extensions, SSE, and the PowerPC-related Altivic, also known as VMX.K, Hardware Performance Counter. Many modern architectures, including embedded ones, often include hardware performance counters, HPC, which enables low-level, instruction-level, collection, benchmarking, debugging or analysis of running software metrics. 74.75 HPC may also be used to discover and analyze unusual or suspicious activity of the software, such as return-oriented programming, ROP, or SIG return-oriented programming, SROP, exploits etc. 76. This is usually done by software security teams to assess and find malicious binary programs. Many major vendors, such as IBM, Intel, AMD, and ARM etc., provide software interfaces, usually written in C/C++, that can be used to collect data from CPU's registers in order to get metrics. 77. Operating system vendors also provide software like Perf, Linux, to record, benchmark, or trace CPU events running kernels and applications. Virtual CPUs. Cloud computing can involve subdividing CPU operation into virtual central processing units. 78. VPS. 79. A host is the virtual equivalent of a physical machine, on which a virtual system is operating. 80. Hwinth are several physical machines operating in tandem and managed as a whole. The grouped computing and memory resources form a cluster. In some systems, it is possible to dynamically add and remove from a cluster. Resources available at a host and cluster level can be partitioned out into resources pools with fine granularity. Performance. The performance or speed of a processor depends on, among many other factors, the clock rate, generally given in multiples of hertz, and the instructions per clock, IPC, which together are the factors for the instructions per second, IPS, that the CPU can perform. 81. Many reported IPS values have represented peak execution rates on artificial instruction sequences with few branches, whereas realistic workloads consist of a mix of instructions and applications, some of which take longer to execute than others. The performance of the memory hierarchy also greatly affects processor performance, an issue barely considered in MIPS calculations. Because of these problems, various standardized tests, often called benchmarks for this purpose such as SPEcint, have been developed to attempt to measure the real effective performance in commonly used applications. Processing performance of computers is increased by using multi-core processors, which essentially are plugging two or more individual processors, called cores in this sense, into one integrated circuit. 82. Ideally, a dual-core processor would be nearly twice as powerful as a single-core processor. In practice, the performance gain is far smaller, only about 50%, due to imperfect software algorithms and implementation. 83. Increasing the number of cores in a processor, i.e. dual-core, quad-core, etc., increases workload that can be handled. This means that the processor can now handle numerous asynchronous events, interrupts, etc., which can take a toll on the CPU when overwhelmed. These cores can be thought of as different floors in a processing plant, with each floor handling a different task. Sometimes, these cores will handle the same tasks as cores adjacent to them if a single core is not enough to handle the information. Due to specific capabilities of modern CPUs, such as simultaneous multi-threading and uncore, which involve sharing of actual CPU resources while aiming at increased utilization, monitoring performance levels and hardware use gradually became a more complex task. 84. As a response, some CPUs implement additional hardware logic that monitors actual use of various parts of a CPU and provides various counters accessible to software. An example is Intel's Performance Counter Monitor technology. 2. See also Technology Portal Addressing Mode, AMD Accelerated Processing Unit, Complex Instruction Set Computer, Computer Bus, Computer Engineering, CPU Core Voltage, CPU Socket, Data Processing Unit, Digital Signal Processor, Graphics Processing Unit, Comparison of Instruction Set Architectures, Protection Ring, Reduced Instruction Set Computer, Stream Processing, True Performance Index, Tensor Processing.
Good. So that was only one part. The video splits in 40 seconds, so we don't have time. I have to look this document for some links, and it's 4 p.m. so I will stop the video. Stop the video, then I will upload, then I will find a new PDF. So let's read some more.